Jiuya Wang give her final lecture on number fields and function fields.
Okay. So, record. Okay, so in the last lecture, I'm going to talk about the function field and number field analog. This is such an exciting direction which we see so many progresses nowadays. So it feels at least some of us should mention it. On the other hand, I am not as actively working along this direction for most of the time. So I will just give a couple examples which actually uses most of the earlier ideas in the function field direction that I feel helpful to my understanding towards some questions. So where do we start? So yesterday we looked at these interesting distribution of class groups, and we have seen the little number of cases we can prove over number field, and over function field. It usually, I think, come with at least two benefits. One benefit is that you have a very powerful tool where you can prove a lot of results, a family of results. Okay. And another benefit is that you can see through the mechanism why something should happen in a more transparent way. Okay, so let's say, for example, we don't get these Mahler's conjecture over number field where interesting questions are requiring. So what can we learn from these questions over function field? And this is related to one of the two issues we see at the end of last lecture. So we need to set up our question. And there are some very basic things that is slightly different on the two sides. So to make the formulation of the question reasonable, let's just quickly go through the analog, where our base field will be the rational function field, and unless there are really strange reasons, we always stick to this as our infinity place, meaning the infinity place is chosen to be this prime ideal if you look at it as FQ join 1 over T. And the finite primes correspond to irreducible polynomial. And when we talk about a discriminant for a number field, we can do this locally, and the local fields have well-defined discriminant that we will adopt here. The only confusion is whether you choose to include the ramification at infinity or not. So I would say, roughly speaking, this is the discriminant, which is a linear in the genus. If you choose to do your option at infinity, it only makes a small change for our problem. Okay. So for what I'm going to talk about today, this does not make a difference. Okay, it does not do discriminant locally at all places or just at finite places. For us, it's going to make a small difference because now let's define our question. Okay, so you can see this is the similar set for us to look at. And the discriminant of field is Q, let's say small, equal to 2 to the m. Then this say, the question is we want to look at this asymptotic behavior as m approaches to infinity. The reason that this is not so important for us here is that you just don't always get a limit as a number field setting. This can be easily understand from some small examples like a C3, where you can have some m that just do not have any discriminant supported there. So due to that reason, we are not going to considering the precise asymptotic with just A and B. In analogues conjecture, which means now if you just modify locally at one place a little bit, it really does not change what your A and B is. Okay. There is some interesting development for these questions originating from a number field case, which is the counterexample that is discovered by Kuhners. And so let's say if you consider this particular commutation representation over rational number field, then the original conjecture, so I will not say the original, just the B constant that we defined on the first day, is not large enough. And this is well understood why by Kuhners, which is this larger family come from fields containing roots of unity over Q. Okay. And the input from function field is that the idea of Ellenberg-Vancash, where they look at this situation, they look at the Malus conjecture over function field where they discuss only the extensions not containing any roots of unity. The extensions over Q1P not containing any constant extension. The A and B constant should be right under the following assumption or heuristic. That if you have an irreducible variety over FQ, then the number of rational points over Q to the n, where n is the dimension, should be 1. So basically, this is the starting point of many calculations. Okay, so what is the idea there? Something nice over function field is that if you look at the field extensions over rational function field with a particular discriminant, then it has this equivalence of category to G covers of P1 over FQ with the degree of ramification Q to the M. And what is actually really nice and useful is that this is parameterized by the Hurwitz space with the chosen number M. Okay. And if we look at over FQ, then this is just FQ rational point for the Hurwitz space. And this Hurwitz space is, there's a natural map. The board is not long enough, it should really be there. You can just, from a G cover, forget about just look at the ramification locus, and that gives you a map from the Hurwitz space to the configuration space. So just ramification locus. And this is going to be the main map that we are going to take advantage of. So what are we going to do? Our goal is to understand the rational point here. And it is realized as some top cover for the configuration space. And just like the Euro-Galois theory, if you have an absolute Galois group acting on some extensions, it's going to be transitive. And now for this covering space, you just need to look at the number of orbits to understand how many component is above. Okay, so consider the action from the fundamental group of configuration space to on this Hertz space, this number of orbits is giving us the number of connected components. And by the assumption, for each component, you roughly just get q to the n many points, then we can get an understanding how many rational points are there for the Hurwitz space. Okay, so assume Q is very large. We just need to understand the number here. So how do we parameterize points in here? Here is the first thing you can try, which is like we do in counting abelian extensions. You just choose your ramification behavior. Yes. For a tuple of conjugacy class, we first look at G covers that is having the exact ramification that inertial group is in the C1 at one point, and just for each point have the corresponding ramification behavior. So this has a name called the Nielsen class. So really just the ramification behavior. We can look at all possible tuples in principle, but just like in the abelian case, you can see not every choice is legal because, for example, if you look at C3, then you really need your prime to be 1 mod 3 to be a legal map. So this is captured by what we call the rationality. Okay, we say you see is FQ rational if Ci to the cube is still the same Ci for each I. And the fact is that over this rational function field, only these ramification behavior are legal. Otherwise, you are not going to see any covers. And then, now, this is the first step. And then second step is now you just look at those classes that is illegal. Okay? the points in the Hilbert space that satisfying those ramification condition. And there are works on these reaction constructing nice properties of the Hilbert space just with this particular ramification behavior. So we can assume all nice properties we're going to use is hold. So now for these, special ramification behavior, how do we understand the number of connected components? Then it's just the idea that we have mentioned before. Now, you parameterize points in the upstairs by tuples of elements, the group elements in your conjugacy class. And basically, because these are covers over P1, you need to add the condition that all these ramifications, when they multiply together, they're trivial. And what is important for us is that this GI needed to generate the whole group in order to consider those extensions with no constant in the fields. And now you can use your fundamental group from the bottom to act on it. That is the braid group, which is a very useful group to look at. The action on the set is that if you look at the generator sigma I, which means you just switch the I and I plus 1 strand, then this is mapping G1 through GK to G1, okay, get this right, GI plus 1, GI inverse, GK, I think the okay, so GI, let's say, wait. Okay, so you can get this correct with just a little bit, basically the product of this should cancel and exactly get 1. And under this action, this is the combinatoric question at call is that you want to ask yourself, for this set with this particular action, how many orbits are there? And this is going to be the number of connected components. And this combinatoric question, for each particular one, you probably can ask computer or use hand, but in general, is not completely trivial. But we can get some approximate answer. Roughly speaking, if your K is large enough, and the number of conjugate class the particular conjugacy class in the class C is large enough for each conjugacy class, then this orbit number can be bounded from upper bound and the lower bound in a uniform way. Bounded uniformly with some constant. Okay. What this tells us is that if you don't care about the constant, then when you look at your generating series for the number of extensions, okay, let's write it in this way. If you look at the generating series where the top is a number of extensions with discriminant q to the n, and this is going to be just approximately the number of legal class over q to the ns, and this means that in order to count all the G extensions, you just need to form the analogue series. Okay. Up to some constant that we don't control, and the generating series which is just coming back to the first question, how many legal classes are there?
Sorry, what is this condition of script C container?
So in this class, these things doesn't need to be different. You just need each conjugate class to appear many times, up to some constant, like larger than some constant, then that's good enough. It turns out the number, this is Mahler-Bagala series with the legal constant is exactly how we define the A constant and the B constant in the beginning. Are exactly correct when we just look at those G extensions not containing constant extension. Okay, this is an expectation since we have assumed the Q very large, and we have assumed that each connected component has just a Q to the n many points with no explicit control on what is the error. But very nice, this is almost the same that modulo the issue of Kluner's example. We are probably fine. And so the next natural thing to do is to look at the other G extensions. And this is done by Tocali that in the sense that he computed this B constant for G extensions satisfy a particular property, which are described in this diagram, which is all the G extensions that makes this diagram commute, where this is corresponding to some constant extension, and this lifting has the property that if you look at the field, it defines its intersection with the constant extension is exactly the one you start with. Okay. So here, what is understood is the orbits of these legal classes. Again, not the combinatoric questions I just erased. So even though we know that Tocali's conjecture based on this calculation is not always true for normal field due to existing problem, at least. We can still learn from this and inspired by this idea. Which is now with the same diagram, if you replace FQ adjoint T by GQ, now here, instead of a constant extension, you put some subfields of your interesting cyclotonic field. In order to make this a finite sum, you only look at those cyclotomic fields that has interesting interaction with your Galois group, and you ask similar condition here that their intersection is exactly when you lift it to a higher mass. Okay, doesn't change. Great. Then we should look at those finite disjoint union of families separately. The more recent progress along this whole story is that we now have much more powerful way to understand this initial heuristic from algebra vantage. And the combinatorial question that is on this board is now following the ideas starting from DVW and Wood and Jiuya Wang Wood, this tells us how accurate we can carry over the orbit calculation here. So previously, we just say, okay, there's some number that we do not know, but this can be understood from nowadays technique. And the complement to that, another recent work of Lanzmann and Levy, they actually turns the heuristic to theorem. By effectively controlling the initial assumption that we made. Yeah? So it's the familiar setup for some people here that you apply these trace formula and understand the stability of homology in the Hertz space. But these are all fantastic results that we hope we can use to understand more and more questions. Now, how about the other side of the world? For the class rule problem. I should say that many of the recent work on the function field side for this class group distribution problem or adopt the idea of moment. These results are very nice, but as I promised you that from yesterday, I want to tell you why the second issue comes up. So I'm going to follow another earlier idea and see why this has to be the case in a relatively quick way. So from the talk yesterday afternoon, we look at the general symplectic group, and they are of interest because whenever we have a function field over normal field, you can look at the algebraic curve and it's Jacobian, so you will see the Frobenius always lands inside the general symplectic group. And this is describing the similitude map where the kernel is just a special symplectic group. Our Frobenius has a nice property that its image down there is always Q, where Q is your FQ joint TU. And the P has nothing to do with Q. P is another Q in this picture. The heuristic is that this Frobenius should be equidistributed among all elements with image here equal to Q. Okay, so that is what we expect to be the case. And you can study the matrix and understand the distribution. But there is a quick observation that if Q is 1 mod P, i.e. if the root of unity is containing your base field, then our Frobenius will have to be contained inside the kernel. If you look at just the mod P level. And when Q is 1 mod P, the special property for these eigenvalues for these finite field matrices have these roots eigenvalue that is symmetric to each other, alpha and alpha inverse. So if you have some eigenvalue 1, you will see another eigenvalue 1 in pair. That means when you look at the co-kernel of the Frobenius minus identity, which describes the rational point, which is a class group on the function field, this has to look differently. At least different from some random matrix we talked about the day before, like say n by n matrix, where you just don't have any tension between different eigenvalues. And this is not just a heuristic. For quadratic field, this is literally true. I should say this is the original idea of Friedman Washington, and it is actually a theorem. It is true for quadratic fields, and this can be seen from looking at the tau sheaf formed from the Jacobian for your hyperbolic curve, where the fiber for each hyperbolic curve, which has a bijection just to the ramification locus because quadratic field is just the Jacobian for that particular quadratic field. The nice property comes up due to a result of JKU, that if you look at the fundamental group of your base acting on the fiber, which is called monodromy group, the monodromy is really large. In fact, it is 4, which means you get exactly what you expect. You hit surjectively to the symplectic group if you look at the geometry part. And then the Frobenius for each particular quadratic field in this setup will be corresponding to the local Galois group for your base. And that you can see from, therefore you can see from some effective chapter of density that you actually get the equidistribution like equidistribution for Frobenius in a normal field, where every term dependence on Q is 1 over root Q. Okay. This again means if Q is large, then we actually get the equidistribution among the symplectic group, which have to have different structure. And then you can ask, if I don't have a wheel pairing, what do you say? And in fact, all of these phenomena still holds over number field, which is so far only supported by numerical result, but a recent work of Will and Sullivan and Wood, where they study this RT48 fundamental class, a completely new object for number field. Okay. New that can be defined for number field as well, that provide evidence that this should also be true over number field. Okay, so a comment from this very explicit result is that, well, unlike those moment results, you can read off the Frobenius from the map directly, which means you actually get the probability distribution without understanding the moment. I never remember what is this probability. And the reason is it is just really not looking good. And I probably, okay, so maybe a lesson that we learned from all these questions probably is that whenever you see new structures imposed on the algebraic question, the distribution will contain new input. And if you don't find the correct structure to look at, then the number just don't look good. So I would say the philosophy, which is completely borrowed from these recent new works, is that in order to obtain nice numbers, we need to find enough structure. Nevertheless, this result, so explicit, is still useful, and the reason that I bring it up is exactly because the first issue that we mentioned, and in order to study those other families aside from the geometric families, we expect this kind of picture to be directly useful, and I will stop here.
Jiuya both for this talk and for her